The last video we have discussed about Newton's law of motion, all three, first law, second law, and third law, and conservation of momentum, of course, linear momentum, and equilibrium of a particle, where if there are so many forces acting on a point mass and they all result to net force zero. So now we are going to take two examples related to those all concepts. Here we are going to solve this first example. What is happening here? There are two identical billiard balls, and those balls are striked against a rigid wall with same speed, but at different angles. And then they get reflected without any change in speed. That is, magnitude of velocity remains the same, but yeah, direction is changing here. So number one, what is the direction of the force on the wall due to each ball? Okay, let's take here friction to be zero. Means we are not mentioning anything about friction. So for a moment, we are taking friction to be zero. Then what is the force? And then we have to calculate the ratio of magnitudes of impulses imparted to the balls by the walls. Okay, let's start with this first case where the ball is striking perpendicularly on the wall. Here we can say very easily that if the ball is striking at right angle, the force exerted by the ball will be perpendicular. This is the force exerted by the ball on the walls. Okay, in the second case, if this is the direction of initial velocity or this is the direction of momentum, what is happening here? At this point, we can see that the ball wants to go this way. This is the initial, means a kind of incident ball. And then it has, if it is trying to move along this line, if it strikes the wall, it will exert the force along this line. But what is happening here? This force can be, yeah, resolved into its component. One, we can say the perpendicular component of the force, and another we can say the parallel component. Okay. If we are neglecting the friction here, this component is no longer acting on the wall. Then we have the only component which is the perpendicular component. So in both the cases, the force exerted by the ball by the ball on the wall is perpendicular, a kind of normal force we can say. Okay. The second question is the ratio of the magnitudes of impulses. Okay. So impulse is nothing but change in momentum. Here, huge force is acting within very short interval of time. So we are taking the concept of impulse here. So impulse is nothing but change in momentum. So we have to find out the ratio of the magnitudes of this momentum change here. So in first case here, let's take this reference, this direction to be positive, this we are going to take positive, and of course then this direction, any vector along this direction we will take negative, and along this direction we will take negative. So in case A, what is happening? The initial momentum is along positive x direction, and if we are taking the mass to be m for timing, let's say the mass of this point particle or point object is m. So initial momentum in case A will be, the initial will be m u positive, and after bouncing back, the final momentum is m into minus u. I'm writing here minus mu because along the velocity is vector quantity, and if we are taking velocity along this direction positive, then we have to take the velocity along this direction to be negative. So this is initial momentum and this is final momentum. And now change in momentum in first case, let's say this case is case A, change in momentum in first case will be final momentum minus initial momentum, that is nothing but minus 2 mu. Now coming to the second case, case B, what is happening? This is motion acting in plane, and now it will be convenient to resolve this motion into two one-dimensional motion, and then the things will get easier. So how can we do that? So at this point, let's say at this point, the initial velocity is along this way, and of course we can see that this angle is 30 degree. So what is happening here? this is positive x and this is negative y, and this is initial velocity. Let's say this is u and this angle is 30 degree. So initial momentum, I'm resolving this motion into its component along x-axis and along y-axis. So let's take first along x-axis. So along x-axis, initial momentum will be, look, this is initial velocity, and the entire velocity is not along the x-axis. It has its component along the x-axis. So that component will be u cos 30 degree, and along y-axis, the component is, let's say, minus u sine 30 degree. I have chosen this downward direction to be negative. Okay, this is initial momentum along x-axis. Sorry, initial velocity. If you are multiplying this thing by mass, then it will be initial momentum along x-axis. So let's tabulate these two things along x-axis and along y-axis. Initial momentum in the case of second event, this is mass times u cos 30 degree, and final momentum, sorry, initial momentum along y will be minus mu sine 30 degree. Okay, next, final momentum of the along x-axis. Let's go back to the diagram. Okay, here is the final velocity, and we can see here that its component along x-axis is actually along the negative x-axis is nothing but minus u cos 30 degree, and along y-axis again it is minus u sine 30 degree. So we can say this is minus mu momentum. We have checked here velocity after reflecting from the wall. The velocity along x-axis is now actually along, it is along negative x-axis. So we are writing its component to be minus u cos 30. So, and we are multiplying this thing by n, then we are getting the final momentum along x-axis, and which is minus mu cos 30 degree, and this is, we can see, this remains unchanged. So along y-axis, the change in momentum is 0 in the second case, and along x-axis, the change in momentum is final momentum minus initial momentum. So we can take 2 mu cos 30 degree. Okay, so this is the change in momentum magnitude. We are talking about magnitude. So let's take in both cases. In first case, it is minus 2 mu, and in the second case, here we can see change in momentum in first case, magnitude of that thing is 2 mu, and in second case it is 2 mu cos 30 degree. So we can take ratio of these two things. So it will be 2 mu divided by 2 mu cos 30 degree, or you can take other way. So this is the ratio, and you can calculate what is the ratio in both cases. In case A, change in momentum, that is impulse, and this is in case B. So this is the ratio. You can calculate very easily. This will be 2 by under root 3. Cos 30 is root 3 by 2 now. So cos 30 is root 3 by 2, and these things are going to be cancelled. So this will be 2 by root 3, and you can solve further this thing to get some decimal values. Okay. Now moving to the next question. Here what is happening? A mass of 6 kg is suspended by a rope of length 2 meter from the ceiling. Here it is shown. A force of 50 Newton in the horizontal direction is applied at the midpoint P of the rope. Now, these all things are shown here. Okay. Now we have to calculate the angle. This angle, let me redraw it here. Okay. So what is happening? There is a ceiling and a rope is here. At this point, in the middle, let's say this is 1 meter, and after this, the rope has length 1 meter there, and there is a mass of 6 kg suspended, and we know this mass will have weight of 60 Newton. If we are taking G equals to 10 meter per square second, this will be 60 Newton. This is a kind of force. Okay. And here, as mentioned, there is a force of 50 Newton, which is horizontal. Let's say this point is point P. Okay. So here, this point is point P. And now we have to calculate this angle, the angle with horizontal. Okay, so we can resolve all these forces into their components along x-axis and along y-axis, and then we can apply the our concept of equilibrium. Okay, if this point is in equilibrium, the total forces acting on this point should result to a zero net force. So let's check what are the forces acting on this point. So at point P, there is one force. This we call free body diagram. We are just taking this point P out here, and then we are drawing all the forces acting there. And let's say along this, there is a tension. We can call it T1. And here, there is another tension because of this rope here. So this tension, let's say, called T2. And from here, we can see easily. Below this point P, the system, rope and this mass is also in equilibrium. So we can say that the T2, this tension, is nothing but 60 Newton. Yeah, the weight of this block which is suspended. Okay. Now here we have 50 Newton force and here we have theta. And if this point P is in equilibrium, so let us resolve this thing, taking P to be origin, and we are taking this one x, y, and here this one will be minus y and here minus x. So one component of T1 will be along positive y and that component will be T1 cos theta. And second component will be along negative x and this component will be T1 sin theta. And now if this point P is in equilibrium, then these all forces which we resolved into component, these all should balance each other. That is T1 cos theta should be 60 Newton. I'm leaving unit for timing. And T2 cos theta, sorry, T1 sin theta should be 50 Newton. And now we can see from here T1 sin theta divided by T1 cos theta is nothing but 50 divided by 60. And here, look, if we have written Newton and Newton, these two units are going to cancel each other actually. So we have here tan theta equals to 5 by 6. And then we can calculate theta equals to tan inverse 5 by 6. This will give some value. We can calculate it using calculator. So this is the angle the rope is making, the string is making with vertical when this point P is in equilibrium. So these two examples are for now. And in next video, we will continue our topic law of motion, where we will discuss the different forces, including friction force.